Video course on statistics. From basics to advanced subjects. Dr. Yehia Elmogahzy, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yehia Elmogahzy is the founder and the president of L-Learning LLC, a consulting education organization.
Sampling distribution of sample mean. And verifying the central limit theorem using Microsoft Excel data analysis.
In order to demonstrate how the central limit theorem works in the real world, let us take two examples. One example will represent a population that has a variable that can be assumed to follow a normal distribution. And the other example will be to use a population with a variable that does not necessarily follow a normal distribution. What we see here is the first example. A company has a population of 2,000 employees, pays a normally distributed annual salary of an average of $50,000 and a standard deviation of $10,000. The population salary is as shown in the Excel spreadsheet that you see here. And we will attempt to answer 4 questions that will lead us to the verification process of the central limit theorem. Question number 1, we will select 40 random samples, each of size 10, using Excel sampling procedure. Question number 2, we will select another 40 random samples of size 30 each using Excel sampling procedure. Question number 3, we will determine the mean and the standard deviation of salary of the entire population and of the sample means for both samples, the samples of size 10 and the sample of size 30. And finally, via the outcomes of the 3 questions analysis, we will try to verify the central limit theorem. This is the first case. We have the ID of the different employees in this company. And if we go down, we're going to find that we have 2,000 employees. And in the next column here, we see the annual salary of each employee. So we have basically 2,000 observations of salaries of the people working in this company. Let us take the samples first, and then later on we will do the analysis associated with each sampling distribution. In order to take a random sample from this population, we can follow these steps. Step 1, we will go to data and we will go to data analysis. And we will look for sampling. And as you can see here, sampling is one of the options in the data analysis of Microsoft Excel. We will click OK. And when we click OK, we will have a menu. The first part of it is the input range. And the input range here implies where we want to select the samples that we need. We can either go by the IDs, meaning select the samples by the ID of the different employees, and that will take a little bit longer time because after we select the IDs, we're going to have to match the salaries of the different employees, and in practice that is normally what we do. But to save a little bit of time here, we're going to go straight to the salary column and select our samples from the values of the salary of the different employees. So we're going to block this entire column of salaries. And as you can see here, we are going down to 2000 values. Here is the ID of the last ID of the employees, which is 2000, meaning we are dealing with 2000 values of salaries. And of course we have labels in the first cell, and as you can see here, Excel gives us the option of either selecting a periodic sample or a random sample. We are going to select a random sample, and per our question, the first question, we have to select a sample of size 10. So we're going to type 10 here, and we're going to specify an output somewhere in the spreadsheet to display the values of the first samples. This is sample 1, and as you can see here, we have 10 values. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we just picked a sample consisting of 10 observations from the population of salary of this company. We can then move on to sample 2 by going back to Excel data analysis and go to sampling. And as you recall, Excel always memorize or remember the last procedure we did. So we're going to select OK, and the input range will be the same, and the sample size being random sample is still the same, is 10. All what we have to do here is to simply change the output. So we're going to put the next output next to the first sample or under sample 2 label, and we say OK, and now Excel is giving us another sample. And we going to keep moving to the next sample, sample 3, and let me bold these so you can see the values more clearly. This is sample 3, this is sample 2, this is sample 1. So let us select sample 3 by repeating what we did a minute ago. We're going to go to data, data analysis, and once again Excel will remember that the last analysis we did was sampling, so click OK, and Excel remember the entire input range as you can see here, so we don't have to re-input the entire column of salary values, and it also remember the sample size we put, which is 10. And again, all what we have to do is to change the output to put it under the next label, which is sample 3, and we say OK, and now we have another sample, and we keep doing that until we finish the number of samples required from us. So this is sample 4, and we're going back to data, data analysis, and sampling, and we have the input recalled, we have the sample size recalled, and we just simply going to change our output to place it under the new label, and we say okay, and we have another sample. So what we're doing here is we've been picking samples from the population, each of size 10, and we will continue with these steps until we finish all the samples required. To avoid wasting your time, I have already prepared the different samples that have been selected using the procedure I just described. Here we have each sample with sample ID, sample 1, 2, 3, all the way to sample 40, and all these samples are selected randomly from the population of employee salaries. The next step after that is we will calculate the average of each sample. Now keep in mind that we are trying to develop a sampling distribution of means. So we need the mean value of each sample in order to do that. And the way we do that, we go under the column of sample 1, and here I put a label of mean, and I'm going to press equal, and I'm going to type average, which means I'm planning to get the average of some values. Then I'm going to open a parenthesis, as you can see, and I'm going to go up starting at the first observation of this sample and go down and close the parentheses, and that will give me the average of the first sample. I can repeat the same thing for the next sample, equal average, and I'm going to block between the parentheses all the observation in this sample and the enter. That will give me the second sample average. I can keep doing that, or I can copy the calculation. So I can come here and say edit copy, and I can actually drag or paste the calculation to cover all the samples, and at paste now I have all the averages of all our samples, as you can see here. So these are 40 averages of 40 different samples, each of size 10. Very good. So now we have the original population data, and we also have the averages of 40 different samples. So let us take the average of the 40 different samples and put it side by side next to the data of the entire population. So we're going to come here and say sample means at n equal 10. And what we mean by that is we have samples of size 10 each, and we are going to place their values under this column. That's the values of the means of the sample, not the samples. So we're going to come here, and we're going under here, and we're going to copy these mean values. So we're going to copy the mean values of the different samples that we just calculated. Here we are. Edit copy, and we're going to go to the column we just prepared right here, and we're going to paste those mean values. Now we have to be very careful here, because we are pasting values that have been calculated. When you paste the calculations, that will alter the values. So as a result, you really need to be extremely careful. First of all, what we have here is a row, not a column. But we need to paste a column. or we need to transform this row into a column. So we're going to have to click on the first cell and say paste special. So we need to go to paste special. Now in order to transform the row into a column, we're going to have to press or click or check the box of transpose. Transpose here means converting the row into a column. But remember, we also have calculated values. So we're going to have to click on or check the box of values. And what does that mean? It means we are telling Excel, okay, we need the row that we just saw of the calculated mean values to be placed here only as the values of the mean values, not the calculations. And we also need to transpose it. And when we say, okay, now we have all the mean values, as you can see, of the 40 samples at size 10 placed next to the column of the population annual salary values. Now, the next question, we need to repeat all of this, but at a sample size of 30. So what we need to do here is we're going to go back to data. Of course, we can prepare columns. We can prepare a new sample, sample 1, and sample 2, and so on, as labels for the new samples. And we're now going to select new samples using Excel data analysis. Using the same procedure we did before, but this time we're going to have 30 samples, or 30 sample size each. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we'll put the sample IDs here, and we can go now to data, data analysis, sampling, and we're going to sample again from the entire population. So we're going to cover this entire population. This is our input range. So we're going to cover the entire range here of data. And this time we're going to select a sample of 30. Of course, the random sample is the default, and we have labels in the first cell because we have labels of the original data of the entire population, and then we can place our value or our sample right under the label of sample 1, and we say OK, and now we have 30 observations representing the first sample of size 30. We can repeat the same thing by going to data analysis, sampling, and as I said before, the input range is memorized by Excel, sample size is memorized. We simply have to change the output. We're going to put it under sample 2, we say OK, and then we repeat this for 40 times because we are taking 40 samples, each of size 30, and as you can see here. And we will continue this step 40 times because we are planning to take 40 samples. Now once again, to save time, I already picked all the samples. Here we have, as you can see, 30 observations in each sample, and this is sample 1, sample 2, 3, 4, 5, 6, all the way to 40 samples, as you can see. And just like we did with the first set of samples that was of size 10, we are going to calculate the mean for each sample. So we're going to come at the bottom of the column of each sample, and we place the label mean, and here we're going to say equal average, and we are going to go up here and block the column under the sample 1, only the observation, close the parentheses, and that will give us the first average, or the average of the first sample. We can repeat this for each sample, equal average, and in parentheses we place the data, as you can see here, and we can do that for each sample, or we can copy the calculation and drag it or paste it to the rest of the samples, and now we have the average values of the new 40 samples, each of size 30, as you can see here. Now, as we did before, we are going to take these values here and place it next to the original column. Remember, we have the first column, which is the 2000 data, the entire data set, and we have the second column, which represent the mean values of the 40 samples of size 10. And now we're going to have another column, call it sample means, and we're going to put n equal 30, because we have a sample size of 30 this time. And just like I did before, I'm now going to take the mean values of the 30 samples we developed. I'm locating it now, and here they are. We have all the mean values here of the 40 samples, each of size 30, and we're going to simply block this row here, and we're going to copy the row, and then we're going to this label sample means of sample size 30. We're going to paste the row right here, but into a column. So we're going to have to do what we did before. We're going to paste the special transpose, that will transform the row into a column, then values, and then OK. And now we have the values of the mean of the mean values of the next sample, or the second sample, which is samples of size 30, I mean. So now we have the observations associated with the entire population, which is the first column here, the 2000 values. And we have the sample means of the 40 samples that we selected first. And they were of size 10. And then we also have the sample means of the 40 samples that we selected in the next step, and each was of a size 30. And now we are about to compare these three situations here. The first situation is the entire population data. The second one is the sample means of size 10. The third one is the sample means of size 30. And how we do that, we will use descriptive statistics. So let us perform descriptive statistics to compare between these three values, or three data sets. We will go to data analysis, and we'll look for descriptive statistics. We'll say OK, and we will start with the entire population. That is the 2000 data observations of the entire population. So I'm blocking this as we speak as the input range for the first descriptive statistics analysis. There is label in the first cell, so check labels. We will place our output right here next to the data sets, and we need summary statistics, so we're going to click on this, and what we have here is the descriptive statistics for the entire population. Let me enlarge these numbers here so we can all see it. And as you can see here, we have a mean value of the entire data set of 50,308. Remember, this was the mean of the entire population, about $50,000 salary. And if we look at the standard deviation, we see that the standard deviation is very close to the $10,000 that we thought it will be the mean value, the standard deviation value. So now we have the mean value and the standard deviation of the entire population. In order to verify the central limit theorem, we need to compare these with the corresponding values of the first sample set, or the means of the first sample set, as well as the second sample set. So let us go and repeat the analysis, descriptive statistics, and this time our input range will have to be the first set of means at sample size 10, which are only 40 samples. And let us put our output next to the output of the entire population. We're going to put it here, and of course Excel memorize everything. We have summary statistics, so when we click OK, we get the output for the average values descriptive statistics. Now we need to keep in mind here that these values are the average of averages. So this value here is the average of averages, because keep in mind that what we just dealt with is the sample means. So this is the average of averages of the sample means, or what we call it mu x bar, or the mean of the averages. Also we have the standard deviation, which is also the standard deviation of averages. Okay, because we're no longer dealing with individual values, we're dealing with average values. And this is for sample size 10. Okay, let us repeat this for sample size 30. So we're going to go here and go to data, data analysis, and descriptive statistics. This time we're going to have to change the input range to the sample means of 30, which is this column here. And we're going to place our output again next to the previous two outputs. And we have summary statistics. So we say OK. And this gives us the descriptive statistics of the sample means for sample size 30. Before I go any further, I need to remind you that the first set, or the first descriptive statistics set, was done for the entire population. So this was done for the entire population. And because of that, here is the mean value, here is the standard deviation. And if you go down here, you're going to find 2000, which is 2000 salaries values as was indicated in the entire population. The second set was the mean value the descriptive statistics of the sample means. Now here is the mean of the means, here is the standard deviation of the means for the different means of samples of size 10, and this, as you can see here in the bottom, we had 40 samples. Similarly, for the sample size of 30, here is the mean of all the means of sample size 30. Here is the standard deviation of all the means of sample size 30, and again we have 40 samples, as you can see. So now we have the opportunity to verify the central limit theorem. I might just delete the column in the middle here, so we can only see, let me move this column here, this cell, so we can only see the values of the mean of the three situations. This one here is the mean of the entire population. This one here is the mean of the means of samples of size 10. This one here is the mean of the means of sample size 30. And as you can see, the three mean are more or less equal. So approximately we have equal means. And that is the first part of the central limit theorem, is that if we take different samples from the population and calculate the mean value of the means of these samples, that mean value will be more or less equal to the mean of the population. Now, as the sample size increases, the standard deviation of the means should decrease because the population standard deviation is the same. So as we take samples of larger sizes, then we should expect the standard deviation of the mean values to decrease. So here is the standard deviation of the population. Here is the standard deviation of the means at sample size 10. It's about 3,114. And here is the standard deviation of the sample means for samples of size 30, and you can see it's about half of this. So you can see that we are verifying the central limit theorem in terms of the general meaning of it, that as the sample size increases, the standard deviation of the means decrease, and that is an important element of the central limit theorem. And the other part is that the mean values will be more or less the same regardless the sample size, if these samples are taken randomly from the original population. Now we can try to look at the distributions, or the frequency distributions, or what we call the sampling distributions at sample size 10 and sample size 30, and compare that with the frequency distribution of the entire population. And we've learned how to construct a frequency distribution in the first part of this course. We can specify classes here, and then we can have midpoint or midpoints, and we can have the upper values. Now, after we do that, we look at the minimum and the maximum values for the entire population. Based on this minimum value and the maximum value, we will start constructing our frequency distribution by first constructing a class column. We're starting at 18,000. So we can go, say, at $5,000 class width. So that will be 18 and 5, $23,000. And then 23,000, we're going to 28,000. 28,000, we're going to 33,000. And 33,000, we're going to 38,000. Talking $5,000 class width. And what does that mean? This simply means that our midpoints The first one, we're talking about 5,000, so we add 2,500, so we have 20,500 as our first midpoint, and of course the upper value will be 23,000. So we can add 5,000 to each one of these by calculating or using the Excel calculations. We're going to add 5,000. We can copy this and paste it here. So now we have the midpoint and the uppers calculated. We can copy this and actually paste them corresponding to the different class cells, and that gives us all the upper values and the midpoints for all the classes. We did this before in different sessions, so we should be very familiar with what I'm doing here. Now let us construct now three frequency distribution, one for the entire population, and one for the sample means of sample size 10, and one for the sample means of sample size 30. Now keep in mind that I used the classes based on the range of the entire population, which is the minimum 18,737 and the maximum 82,800. You can see here that the minimum here is 45,000, the maximum is 59. That's narrower than this range here. Range of, as you can see, the value here is much lower range. Here is also, we can see that the maximum and the minimum are narrower in range than the entire population. So this is why we select or we rely on the entire population values to construct our histograms. If we're going to compare histograms or frequency distribution, it is a must that they should be constructed identically, otherwise we just cannot compare. So now we can go to data analysis, and this time we're going to select histogram. We're going to say OK, and we're going to start with the entire population, meaning the 2,000 data observations of the entire population. Here it is. And we're going to select our bin range from the upper values as we discussed in previous session. So our bin range will be this column here, and we can put our output next to that, and we have cumulative and chart output being checked, so you can say OK, and that will give us the first distribution, which is the distribution or the frequency distribution of the entire population. You can see here is very expanded, so I'm going to reduce it a little bit so you can all see how it looks like. Here it is. And as you can see here, this is the parent population. This is the entire data set that we have. And you can see we have a perfect normal distribution here. In fact, I don't need the cumulative curve for now, so I'm going to delete this, and I can customize this a little bit by going to close the gap as we did in previous sessions, and perhaps change the color of the bars, make them yellow, and the borders I'm going to make them black. So this way we can actually see the frequency distribution much better. So what we have here is the frequency distribution of the entire population. So we can say that this is the frequency distribution of the entire population. And of course, we can change this into salary in dollars. And now we have the histogram roughly of the entire population. Now we can repeat this step for the mean values. So let's do that. We're going now to data analysis, and we are going to histogram. This time we're going to use the next column, which is the column of sample means at size 10. That's 40 observations. The bin range is still the same bin range we're using for the entire population. So all what I have to do is simply just to place the output next to the previous one, and that's okay. And let us take a look at this distribution, how it looks like. Now here is the distribution of the sample means, okay, I'm going to cut it here so I can place it under the entire population frequency distribution. I'm also going to reduce it. And again, we don't need the cumulative curve, so we're going to delete it here, and we're going to say that this is the sampling distribution at sample size equal 10. This is simply a histogram of 40 samples, sample means. We can also customize this a little bit, reduce the gaps, and change the color of the border and cells. And we can see here there is a big difference between the sampling distribution or the histogram of the sample means and the histogram of the entire population. The first thing we can notice here is that the sampling distribution of the sample means is much narrower than the frequency distribution of the entire population. Why? Because as we showed before, the standard deviation and the range for this distribution is much less than the standard deviation of the original population. Now we can repeat the same thing for the other set of samples or sample means of sample size 30. We're going to go to data analysis, histogram, and we're going to this time change the input range to this column here of the sample size 30, and our bin range is the same uppers. We're simply going to place this right next to the previous outputs. We're going to say okay, and we're going to see a much narrower distribution here. In fact, here is a distribution at sample size 30. I'm going to place it under the previous two distributions. So I'm coming here and I'm going to put it right under these, and I'm going to customize it just like I did the previous ones. We're going to eliminate the cumulative curve, we don't need it. We're going to reduce the bars or reduce the gap or eliminate the gap between the bars. We're going to give this a color, say orange, and the bars or the borders, we give it the color of black color. And now we have a new distribution of, or a new sampling distribution. This is a sampling distribution at sample size equal 30. And nothing better to verify the central limit theorem than what we see here. This is the distribution of the entire population. This is the frequency distribution of the entire population. Now, when we decided to take small samples from this population of size 10, we found that the mean value is basically the same. Here is again at the 53, and when we decided to take even larger sample, we have the same center, but the difference between the three distributions lies in the width of the distribution. This one is very wide because it represents the entire population. This one is much narrower because it represents sample means at sample size 10. This one represents a narrower distribution because it represents sample means at sample size 30. Also, you should notice that the sampling distribution is more or less a normal distribution. It may not look perfectly normal because these are real data, but you can easily approximate them as a normal distribution. In fact, if I change the chart type here into a line graph, I'll be able to see a more or less a form of a normal distribution, implying that what we are getting here is a normal, more or less a normal distribution as a result of the central limit theorem. Keep in mind that these all came from a real normal distribution, which is this one here, which is the entire population. So you start with a normal distribution population, you end up with sampling distribution that's more or less normal by virtue of the central limit theorem. Now we are moving to a different problem. This problem, we will see that the parent population is not exactly a normal distribution. Here we have another company of 1,500 employees. It pays an annual salary that ranges from about 27,000 to 140,000. And we are about to do the exact same steps for this new data set representing a new population. So let us go and see what we can do about this. Here is the new data set. And here we have only 1,500 observations, because we have in this company only 1,500 employees, as you can see here. And these are the values of their salaries. So we're going to repeat everything we did in the previous problem. We're going to first select random samples from this population. We're going to start at a random sample of 10. So here is n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go to data, data analysis, and we're going to go to sampling. Press OK. And here is our input range, all the salaries of the 1,500 employees. And we're going to select a random sample of some sample size 10, and we're going to put our output under or right here, and we're going to label this as sample 1. And of course we're going to repeat this process 40 times. I know it's time consuming, but that's the only way to prove the central limit theorem using actual practical values. Of course, we're going to go now to sample 2, and we're going to go to data, data analysis, sampling. Excel, remember what we did before. We simply have the entire input here. We have a sample size of 10. We're simply going to change the output, and we have another sample of 10, and we're going to repeat this 40 times. Here are the 40 samples, each of sample size 10, taken from this new population. The next step is we need to take samples of sample size 30. So we're going to have the first column here, N, 1, 2, and we're going to have 30 IDs or 30 sample size. I went too far, so here is our 30 components of each sample. And here we're going to place the samples that we select randomly. So this is sample 1, this is sample 2, sample 3, and so on, 40 times. We have to do this 40 times because we are selecting 40 samples. And I'm going to repeat the analysis just to confirm what we did before. Here is data analysis, sampling. We still have the same input, which is the entire population. This is the entire population. As you can see, we have 1,500 observations we are selecting from. So nothing changed as far as the entire population. We have random sample. This time we're going to change the 10 to 30 because this time we are selecting 30, our sample size of 30, and we're going to place our output for sample 1 under here, under this label. Here is our first sample. We're going to repeat this analysis 40 times to select 40 samples. All what we have to do is just to go back to Excel, data analysis, sampling, and we change the output to place it under each sample. As you can see, this is an almost automated process and you can do it in a few minutes. And as you can see here, I already selected the 40 samples, each of size 30, as you can see. And of course you are expecting now what we're going to do next. This is the first set of samples of size 10. We're going to calculate the mean of each sample. So we're going to press equal and we're going to type average and open a parentheses, and we're going to block the data associated with the sample 1, close the parentheses, and that will give us the average of the first sample. We're going to copy this and go across all the samples to get the averages of the 40 samples. We need to do the same thing for the second set of samples, which are the samples of 40 samples of 30 sample size. So we're going to click type equal average, and we're going to plug the 30 observations of sample 1 between the parentheses, and that gives us the average of sample 1. We're going to copy this and paste it across all the samples, just like we did in the previous problem. And once again, we have mean values of 40 samples at sample size 30 here, and we have mean values of 40 samples at sample size 10. So we're going to take this row here, and just like we did before, we're going to copy this row and we're going to place it next to the entire population data at this column here. And as I mentioned before, in order to do that, we have to be very careful because these are calculated data. So we're going to have to use paste special. So I'm going to click here and say paste special. And if I check the box of values. That means I'm going to receive values only, not calculated values. And I'm going to transpose, because that was a row and I need to transpose it to a column. And here we have the 40 observations of mean values, the 40 mean values of the first sample set. So these are means at sample size of 10. Okay, I need to do the same thing for the sample size of 30. Here are our mean values. So I'm going now, these are 40 values because we have 40 samples, as you know. I'm going to the sample set of sample size 30, and I'm going to copy the column here, the row of all the sample means. And I'm going to place it next to the previous column of sample size 10. Again, paste the special, transpose, and the values. And now I have another column of mean values of sample size 30. So we basically repeated what we did in the first problem exactly. We went to the entire population here and we took small samples of sample size 10. We took 40 of these. We calculated the mean of each sample, and this is the column of the mean values of the 40 samples we took from the entire population at sample size 10. Then we went back and we took samples each of size 30, and we took 40 of these, and then we calculated the mean value of each sample, and this is the column of the 40 samples of size 30. And to verify the central limit theorem, we have to perform descriptive statistics first on the entire population, then on each sample sets. So we're going to go here and say data, descriptive statistics, data analysis, descriptive statistics, and we're going to say OK, and our input range will be the entire population, because that is the first set we're going to perform descriptive statistics for. So we are going to the entire population of 1500 values here, and we are selecting our output right next to the columns here, and we have summary statistics, and that gives us the descriptive statistics of the entire population. So let me just find the space here by inserting rows so we can widen the space here. Then I'm going to repeat the analysis, descriptive statistics, but this time for the next column, which is the samples of size 10, the 40 observations, and I'm going to put the output next to the previous one, and I'm going to repeat the analysis, descriptive statistics, this time for the column of sample size 30, the 40 samples, and I'm going to place my output again next to these. So now I have three outputs of descriptive statistics, one for the entire population and one for the sample means of sample size 10. So this is the entire population, this is the sample size 10, and this is the sample size 30. Let me just eliminate the middle columns here so we can only see or compare the data. And one more time, we are trying now to verify the central limit theorem. Look at the average value here. The average value of the entire population salary was about 56,000. And as you can see here, and these are real data, The average here did not really change much. It's about 56 something. Here is about 57. So we can see here that the average values did not suffer much change from the entire population. These are the average of averages. Of course, theoretically, the average of average should be exactly equal to the average of the entire population, but since these are real data, we don't expect that. We just expect it to be very close, as you can see here. Now, if we go to the standard deviation, we can see that the standard deviation of the entire population is here. And notice what will happen when we use sample means of sample size 10. This one here was 30,833 standard deviation. At sample size 10, we have 8,630, and at sample size 30, we have 4,878. So you can see here, as the sample size increases, the standard deviation decreases significantly, and that's the essence of the central limit theorem. We can also construct frequency distribution exactly as we did before, and we're going to use the minimum and the maximum of the entire population. Here are the minimum and the maximum of the entire population. So we're going to construct classes based on these values. So let me go here and do classes, and I'm going to start at 27,000. I think since the maximum value is 140, that's a very wide range, so maybe it is wiser to use 10,000. So this will be 27,000. If I use 10,000, so this would be 37,000, I mean, and 37,000 to 47,000. 47,000 to 57,000, 57,000 to 67,000. I'm adding 10,000 every time. So now I build our classes at $10,000 class interval or class width, and I went all the way to 147,000 since the maximum value was 140,000. Now we can do the midpoints. We have 27,000 to 37,000. That is $10,000 interval. Half of that is 5,000, meaning 27 plus 5 will be 32,000. And the upper value is 37,000. We've done all of this before, and then we will add 10,000 to the previous one, the previous midpoint and the previous upper, and then if we copy these and drag it down or paste it, it will give us the midpoints and the upper limits of all the classes we have. Now we are ready to construct frequency distribution. Let us first construct a frequency distribution of the entire population. So I'm going to histogram, okay, and I'm going to the column of the entire population salary, which is this one here, the 1500 values. I'm going to use the upper values as my pen range. And I'm going to put my output next to the upper values here, and this is for the entire population. And if we look at the histogram produced here it is, we will see something really strange. In fact, it is very different than the histogram of the entire range of the first problem we had to deal with. This histogram here, let me just remove the cumulative curve first. This is, as you can see here, is a biased frequency distribution to the low value. You can see that we have high frequencies at the low values, and as we go to the higher values, we have less frequency values. Let me customize this by reducing the gaps or eliminating the gaps. And this is what we called earlier a positively skewed distribution. So now this is the distribution of the entire population. So this is the frequency distribution of the entire population. These are salary values. And now let us do exactly what we did before. We're going to construct histograms for the sampling distribution, or we're going to construct actually sampling distribution. So we're going to go to data analysis, histograms, and this time we're going to the individual values at sample size 10 as our input. And we're going to use the same bin range, and let us put our output again next to the previous output here, and look how the histogram or the sampling distribution look like. Now notice this. Now we have a histogram that looks really strange. Now keep in mind that our full population looked positively skewed. But the sampling distribution, as you can see, let me just remove the cumulative curve here, and I'm going to call this sampling distribution at sample size equal 10. It looks more or less like it wants to be a normal distribution. In fact, if I eliminate those gaps here and change the color, I see a distribution that doesn't look very bad compared to the population frequency distribution. Look at this. This is very positively skewed. This is more balanced distribution. Let us try to construct the frequency distribution at sample size 30. So we're going to go to data analysis, and some histogram, and this time we're going to use the sample size 30. Same bin range. We're going to place our output here next to the previous ones, and let us take a look at how the distribution looks like. Here it is. And what we actually see here is a normal distribution of a very narrow width compared to the previous sampling distribution at sample size 10, and obviously compared to the frequency distribution of the entire population. So what does that mean? This simply means that regardless the shape of the original population. When we take a sample that is large enough, we will end up with distribution that actually looks more or less a normal distribution. And that is the essence of the central limit theorem, that regardless the shape of the original distribution, if we take samples that's large enough, we will reach sampling distribution of normal shape. Obviously, when we deal with real data and real numbers, things do not match the theory perfectly, but it's close enough. And as we mentioned before, by the law of large number, the more we take, the more samples we take, and the larger samples we have, we will approach normality of sampling distributions, and we will also approach a mean value of the sampling distributions that are more or less equal to the mean of the entire population, and the standard deviation of means, the sigma x bar, that is equal to the standard deviation of the population divided by the square root of sample size. It's only a matter of larger samples and the more samples to select.